Hello friends, welcome to this lecture. This will be on evaluating polar double integrals. I've already shared with you some thoughts about the two very important coordinate systems in double integration. One is the Cartesian double integration, the other is the polar double integration. So the fundamentals have been discussed, and the context in which we have to use polar coordinates was also discussed. Let us actually see how it is done, the way one handles polar double integrals, because this is one coordinate system where not many people are comfortable, because we are all familiar working with rectangular grids. So polar grid is something else. It consists of radial lines and concentric circles. So that grid is an unfamiliar area for us, but let us try to understand. So what's the context? It is generally considered convenient to evaluate a double integral using polar variables r and theta when we sense that the region's boundary is made of polar curves. So I've already told you a little bit about what are polar curves and what are so-called Cartesian curves. So let us be very clear about when we are going to shift to polar. Okay? Now these are some simple cases where we can see circles as boundaries of the region, and circles are considered the most friendly of all polar curves. I have already shared with you certain other polar curves which are not that easy to handle, but circle is a very friendly polar curve. So whenever your region of integration appears to be having circular boundaries, I think we must grab the opportunity and apply polar coordinates. And matters are greatly simplified in the polar coordinate system when the function contains x square plus y square. So you can actually guess why I'm saying this, because when we use a transformation x is equal to r cos theta and y is equal to r sin theta, x square plus y square will be reduced to r square. So it will be reduced not only in space of in terms of space, but also there's a reduction in the number of variables. So therefore, one very convenient situation will be when we have polar curves as boundaries of the region, and it will be a bonus if we can also have x square plus y square in the function. So this is just a sample of a situation where polar coordinates can be used instead of evaluating in the original variables x and y. So at the moment, it may not be so clear to you why polar is coming. If you observe that upper limit root of 1 minus x squared, that is an upper limit for y. So when y is equal to 1 minus x squared under root, if you simplify that, you will get x squared plus y squared is equal to 1, which is a circle. So that means circle is somewhere involved as a boundary. And then I was just telling you, the bonus is in the function we have got an x squared plus y squared. So that very nicely reduces the complexity of the problem. So two things I'm trying to impress upon you. One is the boundaries being polar curves. Two, having an x square plus y square in the function. So that is the context in which generally polar coordinates are used. Now, usually the problem is set in the Cartesian frame, and then in case of difficulties, you move to polar domain or some other domain. So what is the procedure to move from a Cartesian situation to a polar situation in double integration? So the first thing is you are given a problem set in the Cartesian framework. Now what you will have to first do is Study the problem for the following features. 1. Whether the boundary involves some polar curve or more than one polar curve. Though it is not mandatory whether x square plus y square is a part of the function. Determine whether the boundaries of the region are forms an Rx region or an Ry region. So those are very, very important decision making tools. Trace the curves, and once all the curves and lines have been traced, they will enclose some region, shade it. Once you are satisfied that, well, the polar coordinate system has to be introduced, then you fix the limits for theta and r. And if you remember my previous lectures, I've already given you some critical diagrams to fix theta limits and r limits. So there are procedures which are available. Then you convert the given Cartesian double integral into a polar double integral. And then of course you will have to evaluate, because that's ultimately what we want to do, evaluate the integral. For some reasons we are not able to integrate in the Cartesian framework, but if you pass through the polar route, then you will be able to possibly get the results. So let me give you one example. Now this is a very, very famous problem that arises everywhere. I will not exactly say such a thing will come in probability theory, but something very similar. This is what we call the Gaussian function. And there is one situation where you will have to evaluate integral 0 to infinity e power minus x square dx. Now, this problem through classical integration methods is not achievable. So, you'll be surprised to know that we'll create a double integral context out of this single variable integration. Let us see how. I'll explain the diagram shortly. Now what I'll do is I will call I as my original integral 0 to infinity e power minus x square dx and create a duplicate of that using the variable y. Then I multiply these two and I get I square is equal to a double integral 0 to infinity e power minus of x square plus y square dx dy. Now, if you look at the diagram there, the x limits vary from 0 to infinity and y limits vary from 0 to infinity, which means the entire first quadrant is covered. Now, because there are no bounds for the upper limit, therefore we can visualize that first quadrant in any shape that we like. Because we are trying to use the polar philosophy, therefore I will visualize the entire first quadrant to be a big circle in the first quadrant. When I say big, I mean the radius of that circle is infinity. So 0 to infinity of x and y means that the entire first quadrant being visualized as a big circle. I mean a big quadrant of a circle of radius infinity. And you know, that is a very appropriate situation to transform to polar. So I'm using the transformation equations, x is equal to r cos theta, y is equal to r sin theta. That leads to x square plus y square is equal to r square. The Jacobian is r, which all of you are aware of. Therefore, the area element dA is equal to dx dy in Cartesian, but we are not able to crack that problem in Cartesian, so we'll try to put it into polar and call dA as r dr d theta. You have seen in the diagram before that the region is completely in the first quadrant, so theta varies from 0 to pi by 2, whereas r varies from 0 to infinity. So your I square problem, which is originally in the Cartesian frame as 0 to infinity, e power minus of x square plus y square dx dy, which for some reasons we are not able to solve, is now converted into a polar double integral with theta limit 0 to pi by 2 and r limit 0 to infinity. And you can now see the function it is now e power minus r square, and dx dy, which is the area element in Cartesian, is now r dr d theta in polar. And we'll have to integrate this. I've not shared the details here, but it is not that very difficult, and the output is pi by 4. But that is I square, I, which is the original problem from 0 to infinity e power minus x square dx, will be the square root of pi by 4, which is root pi by 2. And that's a very, very famous result. I have one more illustration for you. The problem is to find the area enclosed within x is equal to 0, which is a y-axis, outside x square plus y square minus 6x is equal to 0, and inside another circle, x square plus y square is equal to 36, but confined to the first quadrant. So this is the graphical representation of this scene. X is equal to 0 is a y-axis. Then you got that semicircle x square minus 6x plus y square is equal to 0. This will have center at 3, 0 on the x-axis, radius 3 units. And then we have x square plus y square is equal to 36, which is a big circle with center at the origin and radius 6 units. So the region between x is equal to 0, x square minus 6x plus y square is equal to 0, and x square plus y square is equal to 36. So that weird region is the region for which we want the area. So this, once again, is a classic situation where polar coordinates can be involved, because the region boundaries involve polar curves, in this case circles. So I'm using x is equal to r cos theta, y is equal to r sin theta. Jacobian is r. Area of the lamina, as all of you know, is given by the simple double integration rule, double integral dA. And you can see I have fixed the theta limits and r limits here. Theta varies from 0 to pi by 2 because that shaded region or the target region is touching the positive x-axis and the positive y-axis. So therefore the spread is from 0 to pi by 2. And r limits, already explained in one of my previous lectures, will be from 0 to 6 cos theta. However, I will clarify this when I actually show the details. So now the area is double integral r dr d theta, because we are evaluating in the polar frame, and I fixed the limits for theta and r, and evaluation is straightforward, and the answer is 9 pi by 2 according to calculus. But let us not forget, such problems were also solved in schools by our teachers. So if you actually see that shaded region, it is easy to calculate. You find the area of the quadrant of the circle, x square plus y square is equal to 36. From that you subtract the area of the semicircle, x square minus 6x plus y square. So let us see. We have got a small semicircle of radius 3 units, and then that is embedded within a very big quadrant of a circle of radius 6 units. So the area is area of the quadrant, therefore 1 by 4 pi r square minus half, or minus area of the semicircle. So therefore it's half pi r square, but the radii are 6 for the big circle and 3 for the smaller circle. And you can see that we achieve the same 9 pi by 2 even through calculus. So at the end, this looks like a toy example, but this gives us faith that we can use these concepts for higher order problems. What do we do after this? Now we know there are Cartesian situations, there are polar situations and double integration, but what if we are not able to solve a problem using these two domains? Then you'll have to think of some other domain. And every time you think of a change of domain, the Jacobian creeps in. So we must understand the context in which we have to think of a change of domain. And we must understand that transformations can be of two types: linear transformations and nonlinear transformations. In linear transformations, generally, I will not say dimensions will be preserved, but at least the shapes will not be too much distorted. Whereas nonlinear transformations will alter the shape of the region, and those are very difficult things to handle. But these are all the things that are going to come up very soon. And how to figure out the problem in the original domain as well as in the transform domain. Which one will be better for a given situation has to be understood. So dear friends, the point so far is double integrals can be evaluated in three ways: in the Cartesian frame, in the polar frame, or in some other frame. And I have given the inputs for all the three scenarios, and we need some real good problem solving sessions so that you will understand the whole thing in a proper way. Thank you.